Welcome. You have nothing to do right now, nowhere to be, and nothing to figure out. Let your body settle into wherever you are resting, and allow your breath to slow just a little. Tonight, we are going to drift together through some of the strangest, most quietly astonishing corners of the universe, worlds and phenomena so extraordinary they barely seem real. All you need to do is listen and let yourself float. At the very smallest scale imaginable, far tinier than any atom, space itself is not smooth or still. It churns and bubbles in what scientists call quantum foam. This scale, known as the Planck length, is so unimaginably small that a single proton would appear as vast as the entire observable universe by comparison. At this depth, space and time lose their familiar shape and dissolve into a trembling, shifting froth. It is the hidden texture of reality itself, humming quietly beneath everything that exists. Even in the deepest emptiness of space, where no atom has ever drifted, something extraordinary is always happening. Pairs of particles flicker into existence from nothing at all, linger for an immeasurably brief moment, and then vanish back into the void. These are called virtual particles, and they are not imaginary. Physicists have measured their effects in careful experiments. The vacuum of space is never truly empty. It breathes, softly and ceaselessly, in a language too small for us to see. Two metal plates placed very close together in a perfect vacuum will be gently pushed toward each other by nothing at all. This is the Casimir effect, and it is one of the most quietly remarkable demonstrations in all of physics. The virtual particles we cannot see fill the space between the plates differently than the space outside, and that difference creates a real, measurable force. Empty space, it turns out, has a kind of pressure, a whisper of energy that reaches out and touches the world. An electron, one of the tiny particles that surrounds every atom, does not simply sit in one place or spin in one direction while we are not looking. It exists in a superposition, a blended, spread-out condition of multiple possibilities all at once. Only when something interacts with it does it settle into a single, definite state. Before that moment, it holds all its possibilities simultaneously, like a note of music that contains every pitch until someone finally listens. A single particle of light, a photon, can travel through two separate openings at the same time and interfere with itself on the other side. When scientists send individual photons toward a barrier with two narrow slits, the photons create the rippling pattern of a wave, as though each one passed through both openings simultaneously. The moment a detector tries to watch which slit the photon uses, the interference disappears. Light, it seems, keeps its secrets only when no one is watching. Two particles can become entangled, connected in such a way that whatever happens to one is instantly reflected in the other, no matter how far apart they are. Scientists have tested this across distances of over 1,000 kilometers, and the connection holds perfectly every time. No signal passes between them. No message travels. They simply share a state, as though they were never truly separate at all. The light entering your eyes tonight left its source long before these particles were ever measured, yet their bond was already woven into the fabric of things. A neutron, sealed inside a material it should have no way to cross, will sometimes simply appear on the other side. This is called quantum tunneling, and it is not a trick or an error. It is how the universe actually behaves at the smallest scales. The neutron does not break through the barrier. It moves through a kind of probability that allows it to exist, briefly, on the far side. Stars themselves burn because of this effect, hydrogen nuclei tunneling through barriers to fuse and release their warmth. For a particle moving very close to the speed of light, time itself passes more slowly than it does for everything around it. This is not a metaphor, it is a measured, confirmed feature of reality, called time dilation. Particles created in the upper atmosphere by cosmic rays should decay before reaching the ground. Yet they arrive in abundance because their inner clocks have slowed. Time, at its deepest level, is not a fixed river flowing the same for everyone. It bends, gently and precisely, around speed. If a quantum particle is observed again and again in very rapid succession, its natural tendency to change or decay is slowed and, in theory, halted entirely. Scientists call this the quantum Zeno effect, named for an ancient philosopher who pondered whether motion could truly exist. Each observation resets the particle back to its known state, like a clock that is always being wound before it can run down. Attention itself, at this scale, becomes a kind of anchor, holding the world in place. Let your body sink a little deeper now. There is nothing to hold on to, nothing to figure out, nothing to remember. Let your shoulders fall away from your ears. Let your jaw unclench, just slightly. Each breath you take is a little slower than the last, a little more effortless. You are drifting, very gently, toward rest. The universe will keep turning without any effort from you tonight. Quantum spin is a property every particle carries, yet it corresponds to nothing in the everyday world and cannot be pictured in any familiar way. It is not a top spinning, not a ball rotating. Those images simply do not apply. Spin is purely a mathematical truth, a number woven into the identity of each particle, describing something that has no shape or motion we can hold in our minds. Scientists work with it precisely and fluently, even though no one has ever truly seen it. There is a rule woven into the fabric of matter itself. No two particles of the same kind may ever occupy exactly the same quantum state at the same time. This is called the Pauli exclusion principle, and it is the reason solid objects hold their shape, the reason atoms build into the periodic table, the reason matter does not simply collapse into itself. It is a quiet law, never announced, never broken, holding the architecture of everything together from the inside. When a star like our Sun exhausts its fuel and collapses into a white dwarf, its electrons are pressed together so tightly that the Pauli exclusion principle itself pushes back. This resistance is called electron degeneracy pressure, and it is the only thing holding the star from collapsing further. The electrons cannot share the same state, and so they push outward with a force that has nothing to do with heat or fire. A white dwarf is held up not by burning, but by the deep mathematics of quantum identity. When certain gases are cooled to temperatures only a fraction of a degree above absolute zero, something extraordinary and unhurried happens. The atoms slow so completely that they lose their individual identities and merge into a single shared quantum state. This is a Bose-Einstein condensate, a fifth state of matter, distinct from solid, liquid, gas, and plasma. It was predicted by Albert Einstein and the physicist Satyendra Nath Bose in the 1920s, and first created in a laboratory in 1995. Inside a Bose-Einstein condensate, thousands or even millions of individual atoms cease to behave as separate things. They share a single quantum wave function, moving and responding as one unified entity. If you disturb one part of the condensate, the whole thing responds together, as though it were a single vast atom. It is one of the quietest demonstrations of quantum strangeness, not a flash or a collision, but a slow, cold merging, a dissolving of boundaries that we usually take for granted. Certain fluids, when cooled to extreme temperatures, lose all internal friction and become what physicists call superfluids. They flow through the narrowest channels without slowing. They pass through microscopic gaps that no ordinary liquid could ever enter. There is no resistance, no drag, no energy lost to motion. A superfluid set spinning in a container will continue spinning indefinitely, never winding down. It is as though the usual cost of movement has simply been forgiven. Liquid helium, cooled below about 2 degrees above absolute zero, becomes a superfluid and begins to do something that seems to defy all common sense. It climbs. Slowly and without any apparent cause, a thin film of liquid helium creeps up the inside walls of its container, over the rim, and down the outside. It is not being pushed, it is following quantum rules that allow it to find any path where energy can be lowered. Scientists call this the Rowland film, and watching it is like watching physics become something close to a quiet magic. When certain materials are cooled below a critical temperature, they become superconductors, and something remarkable happens to any magnetic field nearby. The material expels it completely. Every magnetic field line is pushed out of the superconductor as though the two cannot coexist. This is called the Meissner effect, and it is the reason a small magnet will float, perfectly still, above a superconducting surface. The magnet is not being repelled by force, it is being excluded by the deep structure of quantum order beneath it. A loop of superconducting wire, once set carrying an electric current, will carry that current forever. Not for a very long time, forever, as far as any measurement has ever shown. There is no resistance to drain the energy away, no friction to slow the electrons. Scientists have run such rings for years and detected no measurable decay. The current simply continues, circling in the dark, patient and undiminished. It is a small, still loop of eternity, resting in a laboratory somewhere, carrying its charge through the night. Time crystals repeat their structure in time rather than in space. Most crystals, salt, snowflakes, quartz, arrange their atoms in a pattern that repeats across distance. Time crystals do something altogether different. Their structure repeats across moments. They tick between two or more states in a steady rhythm, driven not by any external clock, but by their own internal quantum order. They are patterns woven not into the fabric of space, but into the fabric of time itself, cycling gently and endlessly, like a slow, silent heartbeat. There is nothing you need to hold on to right now. Let every thought that drifts through your mind pass like a cloud moving slowly across a dark, still sky. Feel the weight of your body settling, sinking a little deeper with each breath. Your shoulders can soften, your jaw can unclench. The day is finished, and it asks nothing more of you. Simply breathe, and let yourself be carried, gently, toward rest. For a time, scientists wondered whether time crystals might violate the laws of thermodynamics. A system that cycles forever without losing energy seemed to suggest a kind of perpetual motion, something physics had long declared impossible. But careful studies showed that time crystals do not violate those laws at all. They are driven by an external pulse of energy and settle into their repeating rhythm without ever doing useful work. They are not cheating the rules of nature. They are simply dancing within them in a way no one had imagined before. Strange metals conduct electricity in ways that no known theory fully explains. In ordinary metals, electrical resistance rises in a predictable way as temperature increases. In strange metals, resistance rises in a perfectly linear fashion with temperature, all the way down to the lowest temperatures physicists can reach, a behavior that no existing framework of quantum mechanics accounts for. The electrons in these materials seem to lose their individual identities entirely, dissolving into a collective behavior that remains, for now, one of the quieter mysteries at the frontier of physics. Topological insulators are materials that refuse to conduct electricity through their interior, yet allow it to flow freely along their outer surface. The bulk of the material is sealed, inert, unresponsive to current. But the surface is alive with electrons moving in protected channels that cannot easily be disrupted. These surface states are shielded by deep mathematical properties of the material's quantum structure, properties so fundamental that ordinary impurities and defects cannot interrupt them. The current simply finds its way around, flowing along the edges like water tracing the rim of a stone. Major fermions are particles with a remarkable and unusual property. They are their own antiparticles. Most particles have a distinct antimatter counterpart, and when the two meet, they annihilate. But a Majorana fermion, if it encounters itself, simply continues to exist. Physicists believe these particles may arise not in the open vacuum of space, but nestled within certain carefully engineered materials, emerging as collective excitations rather than fundamental particles. They are elusive, still unconfirmed with certainty, but the search for them is one of the quieter, more patient pursuits in modern physics. In certain exotic states of matter produced under powerful magnetic fields and extreme cold quasiparticles appear that carry only a fraction of an electron's charge. An electron carries one fundamental unit of charge, indivisible as far as ordinary experience goes. Yet in the fractional quantum Hall state, the collective behavior of many electrons gives rise to new entities that carry 1/3 or 1/5 or even smaller fractions of that charge. These are not broken electrons. They are something new that emerges only when many electrons act together, a reminder that the whole can be far stranger than the sum of its parts. Anyons are quasiparticles that exist only in two-dimensional systems, and they follow rules unlike any other known particle. Particles in our familiar world are either fermions, which refuse to share a state, or bosons, which freely crowd together. Anyons are neither. When two anyons are exchanged, the quantum state of the system does not simply return to what it was, it accumulates a memory of the exchange, a subtle twist that persists. They are particles that remember their history. The universe, it seems, keeps different rules for different dimensions. Inside solid materials, vibrations do not flow as a continuous wave, but travel in discrete, indivisible packets called phonons. When you press your hand against a warm surface, the heat you feel is carried in part by these quantized ripples moving through the lattice of atoms. Phonons behave in many ways like particles. They can scatter, they can be absorbed, they can even interact with electrons. They are not made of matter in the ordinary sense, yet they carry energy and momentum as faithfully as any particle. They are the quiet trembling of the solid world, parceled into the smallest possible portions. Magnons are the quantum counterparts of ripples in magnetic order. In a magnetic material, countless atomic spins align in the same direction, forming a smooth, ordered field. When one spin tilts slightly, it nudges its neighbor, and the disturbance spreads outward as a wave. Quantum mechanics insists that this wave, too, must come in discrete packets, and those packets are magnons. They travel through the material like a whisper passed from atom to atom across a vast ordered crowd. The light entering your eyes tonight left the sun before any of these particles had a name, yet they were always there, moving through every magnet in silence. Metamaterials can bend light backwards, achieving what scientists call a negative refractive index. Ordinary materials slow light and redirect it as it passes through. A straw in a glass of water appears bent because of this familiar bending. But metamaterials, engineered with microscopic structures far smaller than the wavelength of light, can steer light in the opposite direction entirely. Instead of bending away from the surface, the light curves back around, moving in reverse of every expectation. It is as though the material has quietly rewritten one of the oldest rules of optics. A cloak of invisibility is theoretically possible using shells of metamaterial carefully arranged around an object. The idea is elegant in its simplicity. Guide light around the hidden object the way a stream flows around a smooth stone, so that the light emerges on the other side undisturbed, as though nothing were there at all. The object inside would be wrapped in a kind of optical silence. Scientists have demonstrated early versions of this effect at specific wavelengths in the laboratory. The full invisibility cloak remains beyond current technology, but the physics, remarkably, does not forbid it. There is nothing you need to hold on to right now. Let the thoughts that have been circling all day begin to loosen and drift. Feel the weight of your body settle a little more deeply into whatever is beneath you. Your breath is slow and unhurried. Each exhale carries something away, a tension, a worry, a word left unfinished. You have arrived somewhere restful. There is only this soft, unhurried moment and the quiet that surrounds it. Let yourself sink a little further. Rest is already here. Acoustic metamaterials can create regions of near-perfect silence by manipulating sound waves the way optical metamaterials manipulate light. These engineered structures are designed so that certain frequencies of sound cannot pass through them at all. The waves arrive, find no path forward, and are redirected away. Inside such a region, the world grows extraordinarily still. Researchers have used these principles to design barriers that absorb noise without bulk, and to imagine spaces where sound simply ceases to exist. It is a kind of engineered hush, woven into the architecture of matter itself. Photonic crystals are materials with a repeating internal structure that forbids certain wavelengths of light from existing inside them at all. It is not that the light is absorbed or scattered, it simply cannot propagate through the crystal. These forbidden bands of color are called photonic band gaps, and they arise from the same quantum principles that govern electrons in ordinary crystals. The iridescent shimmer of a butterfly's wing or an opal's inner fire comes from natural photonic structures. Nature discovered this architecture long before human engineers did, weaving light-forbidding geometry into the wings of living things. Light normally travels at nearly 300 million meters per second, but inside a Bose-Einstein condensate, scientists have slowed it to just 17 meters per second, a gentle walking pace. This extraordinary reduction happens because the light couples with the collective quantum state of the condensate, moving through the medium as a hybrid of light and matter rather than pure light alone. At 17 meters per second, a beam of light could be outrun by a bicycle, the universe's fastest messenger, tamed to a crawl by the coldest matter ever created. There is a deep, unhurried wonder in that image. Light has also been stopped entirely, frozen in place inside clouds of specially prepared atoms. By using laser fields to control the quantum state of the atomic medium, scientists have brought a pulse of light to a complete standstill, holding its information within the atoms themselves, and then released it again moments later. The light that emerged was the same light that went in, preserved perfectly during its pause. It is as though a thought were held motionless in midair, then allowed to continue on its way. The boundary between light and matter, in these moments, grows beautifully indistinct. Individual atoms have been photographed using electron microscopes, revealing the smallest building blocks of matter as real, visible objects rather than mere abstractions. In these images, atoms appear as faint, rounded glows arranged in orderly rows, like softly lit lanterns in a dark courtyard. The first such images required decades of technological refinement. Today, scanning tunneling microscopes can not only image atoms but move them one by one, spelling words in atomic script. The thought that something so fundamental can be seen and touched and arranged is one of the quieter marvels of modern science. A single atom of cesium, oscillating between two of its energy states, keeps the world's most precise clocks accurate to within 1 second in 300 million years. The cesium atom vibrates 9,192,631,770 times per second, and this rhythm is so perfectly consistent that it defines the length of a second itself. Every GPS signal, every internet timestamp, every coordinated system on Earth traces its heartbeat back to this one atom's quiet, tireless oscillation. The smallest things carry the steadiest rhythms. Atoms are almost entirely empty space. If the nucleus at the center of a hydrogen atom were enlarged to the size of a marble, the single electron orbiting it would be found somewhere near the outer walls of a large stadium. Everything in between is void, vast, open, and unoccupied. The chair beneath you, the air around you, your own hands, all of it is mostly emptiness, held in shape by invisible fields of force. The solidity of the world is an agreement between forces, not a property of the matter itself. You are, in the most literal sense, mostly made of space. Quarks are permanently confined and can never be isolated alone. Every quark in the universe is bound tightly to other quarks, locked inside protons and neutrons by a force that grows stronger the farther apart they are pulled, like an invisible elastic cord that never breaks but never lets go. No experiment has ever detected a lone quark drifting free. The harder physicists have tried to separate them, the more energy pours into creating new quarks instead, always in pairs or triplets, always bound together. The universe simply does not permit quarks to exist in solitude. Quark-gluon plasma recreates the conditions that existed just 1 microsecond after the Big Bang. In the most powerful particle colliders on Earth, heavy atomic nuclei are accelerated to nearly the speed of light and made to collide, releasing temperatures of several trillion degrees hotter than anything in the present universe. At these extremes, protons and neutrons dissolve entirely, and quarks and gluons flow freely together as a single, shimmering fluid. For the briefest moment, a tiny droplet of the primordial universe is born again inside a laboratory. The very beginning of everything, recreated in a space smaller than a single atom. Strange quarks can combine to form strange matter, which some physicists believe may be the most stable form of matter the universe is capable of producing. Ordinary protons and neutrons contain only 2 types of quarks, up and down, but add strange quarks to the mixture, and the resulting material may settle into a lower energy state than anything we know, like a ball rolling into a valley deeper than any other. If this is true, strange matter would be the universe's most settled, most enduring substance. It would not need to decay or transform. It would simply rest, perfectly and permanently arranged, in the deepest quiet matter can achieve. Let your body grow a little heavier now. Let your shoulders settle, your jaw soften, your hands rest open and still. There is nothing left to hold on to tonight. Each breath carries you a little further from the day, a little deeper into rest. The thoughts that drift through are only passing clouds. You do not need to follow them. Simply let them move on. You are safe and still and held. Let the quiet deepen around you and let yourself begin to drift. Strangelets are hypothetical tiny droplets of strange matter, and if they are truly stable, theory suggests they could convert any ordinary matter they contact into more strange matter simply by touching it. A strangelet encountering a proton might absorb it, transforming it, and grow slightly larger, capable of converting the next particle, and the next. This idea, known as the strange matter hypothesis, was taken seriously enough that it was carefully considered before early collider experiments began. Scientists concluded the risk was vanishingly small, and nature itself, through cosmic rays striking dense stars for billions of years, appears to confirm that strangelets pose no such danger. The universe, it seems, has already run the experiment. Neutron stars pack more mass than our entire sun into a sphere roughly the size of a city. When a massive star exhausts its fuel and collapses, gravity crushes its core so completely that electrons and protons are forced together into neutrons, producing an object of almost unimaginable density. A neutron star, perhaps 20 kilometers across, contains 1.5 to 2 times the mass of the Sun, an entire stellar furnace compressed into something you could cross by driving for half an hour. The light from such an object bends visibly around its own surface. You can see slightly more than half of a neutron star at any one time, simply because its gravity curves the space around it. The crust of a neutron star is the stiffest known material in the universe, composed of atomic nuclei arranged in a crystalline lattice under crushing pressure. This crust is estimated to be 10 billion times stiffer than steel. If you attempted to deform it, the resistance would be extraordinary beyond any earthly comparison. Yet even this remarkable rigidity occasionally gives way. Neutron stars sometimes experience starquakes, sudden fractures in their crystalline surface that release enormous bursts of energy in an instant. In those moments, the stiffest substance in the universe cracks, briefly and violently, before settling once more into its deep, unyielding stillness. A single teaspoon of neutron star material would weigh roughly 1 billion tons on Earth. This is not a poetic exaggeration. It follows directly from the density of these objects, where neutrons are packed together nearly as tightly as they can be. All the matter in that small spoonful would once have been part of a star many times the size of our Sun, compressed by gravity into something almost beyond the reach of imagination. The entire mass of Mount Everest could be contained in a space far smaller than a sugar cube if compressed to neutron star density. The familiar world of weight and substance becomes something else entirely at these extremes. Neutron stars can rotate at astonishing speeds, with the fastest known spinning 716 times every second. These rapidly rotating neutron stars are called pulsars, and as they spin, beams of electromagnetic radiation sweep through space like the beam of a lighthouse. Each rotation is so precise and so consistent that pulsars rank among the most accurate natural clocks in the universe. The fastest of them, spinning hundreds of times per second, are called millisecond pulsars, and their surfaces move at a significant fraction of the speed of light. An object more massive than the Sun, turning faster than a kitchen blender, ticking with the steadiness of an atomic clock. When pulsars were first detected in 1967, their signals were so perfectly regular that astronomers briefly wondered whether they were receiving transmissions from an intelligent civilization. The Discovery team, led by Jocelyn Bell Burnell, noted pulses arriving every 1.337 seconds with such metronomic regularity that natural explanations seemed almost insufficient. The signals were quietly labeled LEM Run for little green men. Before the true source was understood, the universe had produced, entirely on its own, a natural object so orderly and so precise that it resembled a beacon. The stars, it turns out, have always been keeping perfect time. Magnetars have magnetic fields 1 trillion times stronger than Earth's. They are a rare and extraordinary variety of neutron star, born from the most violent stellar collapses, and their magnetism dwarfs anything else known to exist in the universe. If a magnetar were placed halfway between Earth and the Moon, its field would erase every credit card and disrupt every electronic device on our planet. The atoms in your body would be distorted at that distance, their electron clouds stretched along field lines. And yet, from across the cosmos, magnetars simply glow, distant, serene, and incomprehensibly powerful. Magnetar 200,000 light-years away once disturbed Earth's ionosphere. In December of 2004, a burst of energy from a magnetar in a neighboring galaxy washed over our planet, briefly ionizing the upper atmosphere as if a second sun had switched on for a fraction of a second. Astronomers detected the ripple in the ionosphere, a thin, fragile shell of charged gas that wraps our world and makes radio communication possible. The event lasted less than a second, yet it left a measurable trace. Something 200,000 light-years away reached out and touched the sky above you. Nuclear pasta inside neutron stars may be the strongest material in the universe. Deep within the crust, where pressure becomes almost incomprehensible, atomic nuclei are squeezed into long tangled tubes and flat sheets that physicists, with quiet humor, have named after pasta shapes: spaghetti, lasagna, and gnocchi. These structures, predicted by computer simulations, are held together by the nuclear force itself, making them roughly 10 billion times stiffer than steel. No laboratory on Earth can recreate them. They exist only in the hearts of collapsed stars, woven from the fabric of matter under pressures our instruments can barely describe. Neutron stars may contain a superfluid core of neutrons that never stops flowing. Deep beneath the rigid crust, where densities become so extreme that ordinary physics yields to something stranger, neutrons may pair together and enter a superfluid state, flowing without any resistance, without any friction, without any loss of energy, forever. Scientists believe this inner ocean of frictionless matter may be connected to a phenomenon called a pulsar glitch, a sudden tiny spin-up observed in rotating neutron stars, as though the superfluid core briefly tugs the crust along with it. Somewhere inside those distant spinning spheres, a river of matter may be flowing that has never slowed since the star was born. There is nothing you need to do right now, nowhere to be, nothing to solve or remember or hold. Let your body grow a little heavier where it rests. Let your breathing find its own slow, easy rhythm, in and out, and in again, unhurried. If thoughts drift through, let them pass like clouds moving across a wide, dark sky. You are held. You are still. The world is very far away. And all of this, the spinning stars, the frozen rivers of matter, the fields beyond imagining, is simply a quiet story carrying you gently towards sleep. Some neutron stars may harbor a quark matter core at their very center. As densities climb toward the innermost heart of these objects, neutrons themselves may dissolve, their constituent quarks spilling free from their usual confinement to form a new and exotic phase of matter. Scientists believe that above a certain threshold of pressure, this transition may occur, a hidden inner world within an already extraordinary object. The outer layers would remain familiar neutron star material, but at the center, something older and stranger may exist, a relic of conditions last seen in the earliest moments after the universe was born. Quark stars are hypothetical objects denser than neutron stars, made entirely of quark matter. If the pressure at the center of a neutron star is sufficient to dissolve all neutrons into free quarks, theorists suggest the entire star might eventually convert, becoming a body composed of up, down, and strange quarks in a single vast drop of strange matter. Such an object would be smaller than a neutron star, yet more massive. Its surface sharp and hard at the boundary where quark matter meets the vacuum of space. No confirmed quark star has yet been identified, but a handful of neutron stars behave in ways that leave the possibility quietly open. Electroweak stars are theoretical objects held up by electroweak burning. In the hierarchy of stellar remnants, beyond the neutron star and perhaps beyond the quark star, theorists have imagined a body so dense that matter is consumed not by nuclear fusion, but by the electroweak force, one of the fundamental forces of nature that normally only operates at extreme energies. An electroweak star would burn through its fuel in roughly 10 million years, a brief and quiet existence by cosmic standards before collapsing further. It would be a fleeting resting place on the long fall toward a black hole, a moment of strange equilibrium between forces most of us will never need to name. Preon stars are speculative objects smaller than a proton yet massing like a mountain. If quarks themselves are composed of even more fundamental constituents, hypothetical particles called preons, then under conditions of unimaginable density, matter might collapse to a scale far below anything currently observed. A preon star would be invisible to any telescope we possess, its entire mass compressed into a region smaller than the nucleus of an atom. It would pass through ordinary matter as though it were not there. These objects remain entirely theoretical, resting at the outermost edge of what physics allows itself to imagine, where speculation and mathematics meet in the dark. Black holes have a singularity, where density becomes mathematically infinite. At the very center of a black hole, the equations of general relativity reach a point they cannot describe, a place where mass is compressed into zero volume, where the curvature of space-time grows without limit, where the familiar language of physics falls silent. Physicists call this a singularity, and most believe it signals not a true feature of reality, but the edge of our current understanding, a place where a deeper theory, not yet written, must take over. The universe keeps its deepest secrets behind horizons we cannot cross, in places where numbers run out and only wonder remains. At a black hole's event horizon, time appears to stop for a distant observer. If you could watch a traveler fall toward a black hole from far away, you would never see them cross that final boundary. Their image would grow dimmer and dimmer, stretched into longer and longer wavelengths of light, slowing to stillness, frozen at the edge of the horizon like a photograph that never quite finishes developing. Time itself, from your vantage point, would seem to halt for them entirely. It is one of the most tender strangenesses of general relativity, that the universe allows two entirely different stories of the same moment to be equally true. Spaghettification stretches any object, falling into a black hole, into a thin strand. As something approaches a black hole, the difference in gravitational pull between its near side and its far side becomes so extreme that the object is drawn out lengthwise and compressed from the sides, elongated into something resembling a long, delicate thread. Physicists gave this process its wonderfully descriptive name with a certain quiet humor. For smaller black holes, the effect is catastrophic near the horizon. For the most enormous black holes, the tidal forces at the horizon are surprisingly mild. A traveler might cross without immediately noticing anything unusual, the strangeness arriving only much later. Black holes evaporate over trillions of years through Hawking radiation. In the early 1970s, the physicist Stephen Hawking made a remarkable theoretical discovery that black holes are not entirely black. Near the event horizon, the quantum nature of space allows pairs of particles to flicker into existence, and occasionally one escapes while the other falls inward. The black hole loses a tiny, almost immeasurably small amount of energy with each such event. Over timescales so vast, they dwarf the current age of the universe many times over. Even the largest black holes would slowly, imperceptibly fade. The light entering your eyes tonight left its source long before this process would meaningfully change even the smallest known black hole. The information paradox asks whether black holes destroy information forever. In quantum mechanics, information about the state of any system is never truly lost. It may transform, scatter, or hide, but the mathematics insists it must persist somewhere. Yet when matter falls into a black hole, and the black hole eventually evaporates through Hawking radiation, the outgoing radiation appears to carry no memory of what fell in. This tension between two deeply trusted frameworks of physics, quantum mechanics and general relativity, has occupied some of the finest minds in theoretical physics for decades. It is not a troubling mystery, but a quiet invitation, a place where the universe is gently asking us to think more carefully, to reach further. The firewall paradox suggests the event horizon may be a wall of high-energy radiation. In 2012, a group of physicists proposed a deeply unsettling possibility that in order to preserve information and honor the rules of quantum mechanics, the event horizon of a black hole might not be the calm, unmarked boundary general relativity describes. Instead, it could be a seething boundary of intense radiation, a firewall that would destroy anything crossing it instantly. The paradox does not resolve neatly. It sits at the intersection of our two greatest theories, neither of which fully yields. Most physicists suspect the answer lies somewhere in a theory we have not yet found, resting quietly, waiting to be understood. Let yourself rest now. There is nothing to hold on to, nothing to work out or remember. Simply allow your body to grow heavier where it lies, each breath arriving a little more slowly than the last. Let your thoughts drift like distant light, present for a moment, then softly fading. You have traveled through remarkable places tonight, and now there is nowhere left to go. The universe continues its slow, vast turning, and you are held gently within it. There is only this breath, and the one after, and the quiet dark that receives you. Let yourself sink a little deeper. Let everything soften. Supermassive black holes, billions of times the sun's mass, lurk in most galaxies. At the heart of nearly every large galaxy in the observable universe, including our own, there resides a black hole of almost incomprehensible scale, not millions, but billions of times the mass of our sun, compressed into a region that would fit within our solar system. These immense objects shape the galaxies around them, regulating the birth of stars across vast distances through jets of energy and radiation. They are ancient, forming in the earliest chapters of cosmic history. Our own galactic center holds one such object, distant, dormant for now, and radiating only the faintest murmur of activity. The black hole known as Ton 618 holds a mass 66 billion times that of the Sun. It is one of the most massive black holes ever measured, residing in a distant quasar, a brilliantly luminous core of an ancient galaxy, so far away that its light has traveled roughly 10.4 billion years to reach us. Its event horizon would comfortably encompass a region larger than the distance from the Sun to the edge of our solar system many times over. It is a structure so immense that the word large no longer quite applies. It belongs to a different order of existence, where familiar comparisons dissolve into something closer to pure stillness and awe. Intermediate mass black holes fill the mysterious gap between stellar and supermassive types. For a long time, observations revealed two distinct populations of black holes, those formed from dying stars, ranging up to perhaps 100 times the mass of the Sun, and the supermassive giants at galactic centers, millions to billions of times more massive. Between them lay a quiet gap, a range of masses for which evidence was sparse and uncertain. In recent years, astronomers have begun to find compelling candidates, objects hundreds or thousands of times the Sun's mass, lurking in dense star clusters and the outskirts of galaxies. They may be the missing link in the story of how the largest black holes grew. Primordial black holes may have formed in the very first seconds after the Big Bang. In the earliest moments of the universe, the distribution of matter and energy was not perfectly smooth. Regions of slightly higher density existed, and under the extraordinary pressures of that infant cosmos, some of those regions may have collapsed directly into black holes before any star had ever formed. These primordial black holes would carry no memory of stellar collapse, no parent star, no supernova. They would simply be children of the early universe itself. Some theorists suggest they could account for a portion of the dark matter that fills the cosmos, ancient and invisible, drifting through the galaxy since nearly the very beginning of time. A primordial black hole, the mass of a mountain, would be compressed into a space no larger than a single proton. All that rock, all that stone, all that weight, reduced not to dust, not to vapor, but to something so vanishingly small it would pass through ordinary matter like a whisper through open air. This is one of the stranger consequences of gravity taken to its ultimate conclusion. Mass does not determine size, density does. A proton-sized object massing like a mountain would carry a gravity so ferocious that nothing around it could remain unchanged, yet it would be utterly invisible to the naked eye, smaller than any instrument of human making could ever directly touch. Wormholes are theoretical tunnels that could connect two distant points in space-time, as if folding the fabric of the universe upon itself. Imagine the cosmos as an enormous sheet. Two regions separated by billions of light-years might, in principle, be brought into contact by bending that sheet until the 2 points nearly touch and threading a passage between them. General relativity permits such structures mathematically. The equations do not forbid them. They arise as smooth, curved solutions in the geometry of spacetime, elegant and unhurried in their mathematics. Whether nature ever actually builds them remains an open and quietly wondrous question. Einstein-Rosen bridges are a specific kind of wormhole that forms within the geometry of a black hole, but they collapse far too rapidly for anything to pass through. When physicists first worked through the mathematics of black holes in the 1930s, they found that the equations described not a dead end, but a kind of throat, a passage that opened and closed in an instant, far faster than light itself could traverse it. It is a doorway that exists only in the language of equations, opening and sealing in the same breath. The universe allows the architecture, but not the journey, at least not without conditions that remain far beyond our reach. A remarkable conjecture in modern physics suggests that wormholes and quantum entanglement may be two expressions of the very same underlying phenomenon. The idea, known by the shorthand linking Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement, proposes that when two particles become entangled, they are connected not merely by correlation, but by a thread of space-time geometry, a microscopic wormhole woven into the fabric of reality itself. If this is true, then the strange quantum connections that link particles across any distance are not separate from the structure of space. They are the structure of space, expressed at the smallest possible scale. The thought settles slowly, like light diffusing through still water. White holes are the theoretical time. Reverse of black holes, regions from which matter and light can only escape, never enter. Where a black hole draws everything inward, a white hole would expel everything outward, a source rather than a sink, a beginning rather than an ending. General relativity's equations permit them just as naturally as they permit black holes. The mathematics makes no distinction between the two directions of time. Whether white holes exist in nature remains unknown. Some researchers have speculated that the Big Bang itself may have had qualities reminiscent of a white hole, an outpouring of everything from a single point, unhurried and complete. A naked singularity is a singularity, a point of infinite density that exists without an event horizon to conceal it from the rest of the universe. In every known black hole, the singularity is hidden behind that boundary, shielded from direct influence on the outside world. But the equations of general relativity, under certain extreme conditions, allow singularities to exist exposed and unshielded. Roger Penrose proposed what he called cosmic censorship, the idea that nature itself forbids naked singularities, always clothing them in horizons. Whether this is a true law of physics or simply a tendency remains one of the deeper unresolved questions resting quietly at the edge of our understanding. There is nothing you need to hold on to right now. Let your thoughts loosen their grip, one by one, like leaves releasing from a branch at the end of autumn. Your body knows how to rest. It has always known. Feel the weight of your limbs settle a little more with each breath, sinking softly into stillness. The mind does not need to solve anything tonight. Let it grow quiet. Let it grow wide, like a sky after the last light has faded. You are safe, you are still, and sleep is already drawing near. Closed time-like curves are solutions to Einstein's field equations that describe paths through space-time looping back upon themselves, allowing a traveler to return to their own past. They are not science fiction. They are genuine mathematical solutions, arising naturally from certain arrangements of mass and energy in the equations of general relativity. Whether the universe permits them in practice is another matter entirely. Most physicists suspect that nature enforces some protection against paradox, some quiet rule that prevents the loop from ever closing. But the equations themselves do not object. They simply describe the geometry, serene and indifferent, and leave the question of possibility to a deeper layer of physics not yet fully understood. Kurt Gödel discovered in 1949 that a uniformly rotating universe is a valid solution to Einstein's equations, and within it, paths exist that lead a traveler into their own past. Gödel was a logician and mathematician, a close friend of Einstein's, and he presented this solution as a kind of gift and a puzzle. If the universe were rotating as a whole, time would not flow in a single direction, but would curve back on itself across vast scales. Our universe does not appear to rotate in this way, so the solution remains a theoretical curiosity rather than a practical map. But it revealed something remarkable: that time's arrow is not written into the equations themselves. It is something the universe chooses, or perhaps something we have simply been fortunate enough to inherit. Frame dragging is the phenomenon by which a massive rotating object pulls the very fabric of space-time along with it as it turns. This is not a metaphor. Space-time itself is dragged, twisted, set into a slow rotation around the spinning body at its center. The effect was predicted by Joseph Lenz and Hans Thüring in the early 20th century, and confirmed by precise satellite measurements in the years since. Around a slowly rotating body like Earth, the effect is extraordinarily subtle. Around a rapidly spinning black hole, it becomes extreme. Space-time itself is swept into rotation, and the region near the equator is drawn inward along a spiral that has no classical equivalent. The light entering your eyes tonight has traveled through a universe where space itself can be made to turn. Gravitational waves stretch and compress space by less than 1,000th the width of a proton. When two black holes spiral together and merge somewhere across the universe, they send ripples through the fabric of space-time itself, and those ripples, by the time they reach us, are almost incomprehensibly small. The detectors that sense them must measure a distortion smaller than a single proton divided into 1,000 equal pieces. It is perhaps the most delicate measurement ever made by human hands. And yet the waves are real, arriving like the softest imaginable breath across the whole of space, carrying news of ancient collisions from billions of light-years away. The first detected gravitational wave signal lasted only 0.2 seconds. On the 14th of September, 2015, two distant detectors registered a faint chirp, a brief rise and fall in the fabric of space-time that lasted less than a quarter of a second from beginning to end. In that tiny sliver of time was encoded the entire story of two black holes, each many times the mass of the Sun, completing their final orbit and merging into one. Scientists had waited decades for that moment. When it came, it arrived like a whisper, fleeting, unhurried in its meaning, even as it was brief in its passing, and it opened an entirely new way of listening to the universe. Neutron-star mergers forge gold and heavy elements in brilliant kilonovae explosions. When two neutron stars spiral together and collide, the violence of that meeting creates conditions so extreme that atomic nuclei are rapidly assembled into the heaviest elements: gold, platinum, uranium, and dozens more. The explosion that follows, called a kilonova, blazes briefly with a warm golden light, unlike almost anything else in the cosmos. The gold in a wedding ring, the iridium in a spark plug, the uranium deep in the earth, all of it was born in moments like these, scattered across space long before our solar system formed. We carry the remnants of those ancient collisions with us, quietly, every day. Gravitational lensing bends light, so that a single distant galaxy can appear as multiple images in the sky. When a massive object, a galaxy cluster perhaps, lies between us and something far beyond it, its gravity warps the path of light traveling toward us. The same source can arrive along several curved routes simultaneously, appearing in 2 or 3 or even 4 separate places at once, like a reflection in a curved mirror made not of glass but of space itself. Astronomers use these distortions to map the invisible mass that bends the light, reading the shape of the universe from the way its images multiply and arc. It is a quiet kind of magic, the cosmos using gravity as a lens to show us things we could not otherwise see. An Einstein ring forms when a distant galaxy aligns so perfectly behind a gravitational lens that its light is spread into a complete, unbroken circle. The geometry must be nearly exact, the source, the lensing mass, and the observer all falling along the same line. When that alignment occurs, the image of the background galaxy wraps all the way around, forming a luminous ring of light suspended in the dark. These rings are rare and extraordinary, and each one is a testament to the precision of general relativity, a theory written on paper more than a century ago, now confirmed in the architecture of the sky itself. There is something deeply restful in that thought, that the universe behaves so exactly as the mathematics describes. Dark matter makes up 27% of the universe, yet it has never been directly detected. It does not emit light, absorb light, or interact with ordinary matter, except through gravity, and yet its presence is felt everywhere, shaping the rotation of galaxies, bending the paths of light, and providing the scaffolding upon which the large-scale structure of the universe is built. Scientists are confident it exists because its gravitational effects are measured and consistent, and cannot be explained any other way. What it actually is, what particle or field or entirely new form of matter gives rise to it, remains one of the deepest open questions in all of physics. It surrounds us, invisible and unhurried, making up more than a quarter of everything there is. Dark matter halos surround every known galaxy, extending far beyond the visible stars and gas. The luminous disk of a galaxy, the part we can see, the spiraling arms and glowing core, is embedded within a much larger invisible sphere of dark matter that reaches outward for hundreds of thousands of light-years in every direction. Without this halo, galaxies would fly apart. The visible matter alone does not provide enough gravity to hold them together at the speeds they rotate. The halo is the true body of the galaxy, vast and unseen, cradling the stars within it, the way a deep ocean floor cradles everything that drifts above it. The light entering your eyes tonight left its galaxy wrapped in one of these silent, invisible shells. There is nothing you need to figure out right now. Let the facts and the distances and the wonders dissolve gently, like mist rising from still water in the early morning. Your breath is slow and even, your body is heavy and warm, settled into the surface beneath you. Each thought that drifts through your mind can simply pass. You do not need to follow it, hold it, or answer it. Let the darkness behind your eyes become wide and deep, like the space between stars. You are resting. You are safe, and with each slow, unhurried breath, sleep draws a little closer, soft and certain, ready to carry you away. The bullet cluster reveals dark matter passing through itself during a collision between two galaxy clusters. When these two enormous structures collided, the ordinary matter, the hot gas, slowed and clumped together, heated by the impact. But the dark matter, invisible and non-interacting, passed straight through, continuing on its path as though the collision had never happened. Astronomers mapped the mass distribution using gravitational lensing and found that most of the mass had sailed through, separating cleanly from the glowing gas left behind. It was one of the most compelling pieces of evidence ever gathered for dark matter's existence, a moment where the invisible left a clear and unmistakable shadow, written across the sky in the language of bent light. Dark energy makes up 68% of the universe and is the force driving its accelerating expansion. Unlike ordinary matter or dark matter, dark energy does not clump or cluster. It is spread evenly through all of space, a kind of pressure built into the fabric of the universe itself. As space expands, more dark energy is created, which drives further expansion, which creates still more. A process that has been carrying galaxies apart from one another for billions of years, and will continue to do so long after any star now burning has grown cold and dark. We do not know what dark energy is. We know only that it is the dominant ingredient of everything that exists, vast and serene, woven into the very structure of space, quietly unfolding the universe into greater and greater distances. The cosmological constant is the smallest non-zero number in all of physics. It is a value so extraordinarily tiny that writing it out would require a decimal point, followed by 122 zeros before reaching the first significant digit. Einstein first introduced it as a term in his equations of general relativity, and though he later doubted it, the universe itself seems to have embraced it, holding this almost imperceptibly small value with breathtaking precision. It is as though the universe were balanced on the very tip of a needle, maintaining this faint, almost silent pressure that shapes the fate of everything. The vacuum energy predicted by quantum field theory is 10 to the power of 120 times larger than the dark energy we actually observe. This staggering discrepancy, sometimes called the worst prediction in all of science, means that the universe we live in is vastly quieter and gentler than quantum theory alone would suggest. Something, somehow, cancels nearly all of that predicted energy, leaving only the faintest whisper of it behind. Scientists call this the vacuum catastrophe, and it remains one of the deepest, most humbling mysteries in all of physics, a reminder that the universe holds its own counsel. The universe's expansion is accelerating, which means that distant galaxies will one day vanish entirely from our view. As space stretches faster and faster, the light from galaxies far enough away will never reach us, not because they are destroyed, but because the space between us grows too quickly for their light to cross. One by one, over hundreds of billions of years, galaxies will slip beyond a kind of horizon, fading and redshifting into silence. Future civilizations, if any exist, may look out at a universe that appears almost empty, with no way of knowing the vast cosmic web that once surrounded them. The observable universe spans 93 billion light-years across, even though the universe is only 13.8 billion years old. This seems impossible at first. How can light have traveled farther than the time it has had to travel? The answer lies in expansion itself. Space has been stretching all along, carrying distant regions far beyond where light alone could reach. The universe is not simply a sphere of light radiating outward. It is a fabric that has been quietly unfolding in every direction at once, carrying matter with it to distances that feel almost beyond imagining. And yet here we are, resting at the center of our own small, luminous window into it all. The cosmic microwave background is the afterglow of the Big Bang, and it is still visible today in every direction we look. About 380,000 years after the universe began, space cooled enough for atoms to form, and for the first time, light was free to travel. That ancient light has been journeying ever since, stretched by the expansion of space into the microwave range, now arriving at our instruments as a faint, even warmth filling the entire sky. It is the oldest light in the universe, a soft, all-encompassing glow that has been traveling for nearly 14 billion years, carrying within it a portrait of the universe in its earliest, most tender moments. Within the cosmic microwave background, there is a cold spot, a region measurably cooler than its surroundings, and some researchers have proposed it may be the imprint of a supervoid, or even the echo of a collision with a neighboring universe. Most scientists favor a more familiar explanation, a vast, nearly empty region of space that slightly cooled the light passing through it. But the cold spot remains intriguing, sitting quietly in the ancient light, neither confirming nor denying the more extraordinary possibilities. It is one of those places in science where the data invites wonder without demanding a final answer, a gentle question mark written in the oldest light we know. The great attractor is an enormous concentration of mass, pulling the Milky Way and tens of thousands of neighboring galaxies toward it at extraordinary speed. Our galaxy is drifting toward it at roughly 600 kilometers per second, carried along with an entire region of the universe known as the Laniakea supercluster. For decades, the great attractor was hidden behind the dense dust and stars of the Milky Way's own plane, invisible to our telescopes. When astronomers finally peered through, they found a vast gathering of galaxy clusters, a gravitational anchor so immense that it shapes the motion of everything around it, drawing the local universe toward it in a slow, unhurried cosmic tide. The Bootes void is a supervoid 330 million light-years across, containing almost nothing at all, where the universe elsewhere is threaded with filaments and clusters and the faint glow of countless galaxies. The Bootes void is simply empty, an enormous hollow in the fabric of the cosmic web, so vast that if the Milky Way were placed at its center, we would not have known other galaxies existed until the middle of the 20th century. A handful of galaxies do drift within it, small and isolated, surrounded by an ocean of space so underpopulated it feels like a held breath. It is one of the most profound silences in the known universe. There is nowhere you need to be right now, no thought that needs following, no question that needs answering. Let your body settle a little deeper into the warmth beneath you. Feel the weight of your arms, your legs, your shoulders, all of it releasing, softening, letting go. Your breath moves slowly, without effort, in and out, like the tide drawing back from a shore. The distances we have traveled tonight, from the faintest whispers of ancient light to the vast and empty hollows of the cosmic web, all of it is dissolving now, drifting away like stars behind a closing cloud. Let your thoughts grow still. Let the darkness behind your eyes deepen and spread. Sleep is very close. You are already on your way. Cosmic filaments are the largest structures in the universe. Enormous rivers of matter spanning hundreds of millions of light-years, connecting clusters of galaxies across the vast reaches of space. They form the skeleton of the cosmic web, a delicate, three-dimensional lattice of glowing threads and nodes, with immense voids between them. Every galaxy we know, including our own, is embedded somewhere within this web, nestled along a filament or gathered at a junction where filaments meet. Seen from far enough away, the universe resembles something organic and intricate, a vast, luminous network that has been quietly assembling itself for nearly 14 billion years, one thread at a time. Hercules, Corona Borealis Great Wall, is the largest known structure in the observable universe, stretching roughly 10 billion light-years from end to end. It is so immense that it challenges one of the foundational assumptions of cosmology, the idea that, at the largest scales, matter is spread smoothly and evenly across the universe. At 10 billion light-years, this structure spans more than 2/3 of the diameter of the observable cosmos, a concentration of galaxies so enormous it should not exist within the framework of how the universe is thought to have formed. Astronomers are still working to understand it, holding the mystery with quiet curiosity rather than alarm. Rogue planets drift silently through interstellar space, untethered to any star, wandering through the darkness entirely alone. They are thought to have been ejected from their home solar systems long ago, flung outward by gravitational encounters with larger planets, or perhaps never captured by any star at all. Without a sun, they receive no warmth, no light. Their surfaces are perpetually cold and dark, wrapped in frozen atmospheres or buried beneath ancient ice. And yet they travel on, unhurried, crossing the vast spaces between stars over millions of years, invisible and solitary, like stones cast into a still, dark ocean. Rogue planets may outnumber the stars in our galaxy by thousands to one, making them among the most abundant worlds in existence. If that is true, the galaxy is filled with an almost unimaginable number of wandering worlds, dark, cold, silent, moving through the spaces between stars in numbers that dwarf every sun that shines. We have only recently begun to detect them, and each discovery hints at a hidden population of worlds, so vast it reshapes our sense of what a galaxy truly contains. The universe, it seems, holds far more darkness than light, and far more solitude than we had imagined. Planet 9 is a hypothetical world, never directly observed, whose existence is inferred from the strange clustering of distant objects at the far edge of our solar system. Scientists believe a large, unseen planet, perhaps several times the mass of Earth, may be orbiting the Sun at an enormous distance, its gravity gently herding a group of smaller icy bodies into orbits that would otherwise make no sense. It would take this world thousands of years to complete a single orbit, moving so slowly and so far away that it remains hidden in the darkness beyond our current reach. It is a ghost planet, known only by the faint gravitational whisper it leaves behind. Hot Jupiters are gas giants that orbit their stars at extraordinary closeness, completing a full year in just a few days, faster than Earth completes a single week. They were among the first exoplanets ever discovered, and their existence baffled astronomers, who had assumed that large planets could only form in the cold outer regions of a solar system. Instead, these worlds hug their stars so tightly that their surfaces are bathed in relentless stellar radiation, their atmospheres sculpted by tidal forces and searing heat. A year on such a world passes before most flowers on Earth have had time to open. Ultra-hot Jupiters are a more extreme class still, worlds so close to their stars that the temperature on their day side reaches several thousand degrees, hot enough to tear apart the very molecules that make up their atmospheres. Water, carbon dioxide, and other compounds that form readily in cooler environments are simply shredded by the heat, broken back into their constituent atoms. The night side of these worlds can be hundreds of degrees cooler, creating a permanent, violent gradient between the two hemispheres. It is a place where chemistry itself is undone by proximity to a star, where the building blocks of matter are stripped bare and scattered on the wind. The exoplanet known as WASP-76b is a world where iron does not sit in rocks or soil, it evaporates on the day side and falls as rain on the night side. The temperature on the sunlit face of this planet is so extreme that iron vaporizes and rises into the upper atmosphere, carried by fierce winds to the cooler night side, where it condenses into droplets and falls as liquid metal. Scientists detected this iron rain by analyzing the light that passes through the planet's atmosphere as it crosses in front of its star. It is a world of quiet, terrible elegance where the sky delivers not water but rivers of molten iron drifting down through the dark. 55 Cancri E is a super-Earth orbiting so close to its star that its surface may be entirely covered by a vast, slowly churning ocean of lava. The planet completes its orbit in less than 18 hours, and its surface temperature is thought to exceed 2,000 degrees Celsius. Scientists believe the intense heat may keep the rocky surface in a permanent state of melt, a world without solid ground, where the landscape is a glowing, sluggish sea of molten rock stretching to every horizon. It is a place that reminds us that the word world does not always mean shelter or stillness, but sometimes simply means a surface, however fierce. Gliese 436b is a planet that defies an easy description. Its surface temperature exceeds 300 degrees Celsius, yet its water remains frozen solid, compressed into a strange, dense form that scientists sometimes call hot ice. The pressure deep within the planet is so immense that it forces water molecules into a crystalline structure that holds firm even at temperatures far above the normal boiling point. It is a world turned inside out by extremes, burning hot on the outside, yet locked in a kind of rigid, pressurized frost within. The light that passes through its atmosphere left that distant star long before the first human city was ever built. Let your body grow heavy now, soft and still. There is nothing left to hold on to, no thought that needs tending, no place that needs reaching. Feel the warmth beneath you, the gentle pressure of rest against your back, your shoulders, the backs of your hands. Your breath moves on its own, slow and even, without any effort from you at all. All of those distant worlds, the iron rain, the frozen fire, the wandering darkness between stars, they are drifting away now, dissolving into the deep, quiet space behind your eyes. You do not need to follow them. Let them go. Let everything go. Sleep is already here, soft and patient, waiting for you to simply stop. The exoplanet, known as HD 189733b, is a world of almost unimaginable violence, where winds howl at 8,700 kilometers per hour, and the sky rains not water, but tiny shards of molten glass driven sideways through the atmosphere. Yet even knowing this, there is something strangely mesmerizing about it. A world so extreme, it has its own terrible alien weather. The glass-laced winds sweep endlessly, silently, across a sky we will likely never visit. The planet known as Kelt 9b is hotter than most stars in the sky, its upper atmosphere reaching temperatures of more than 4,000 degrees Celsius, far exceeding the surface of many smaller stars. It orbits so close to its blazing host star that the star's radiation is slowly stripping the planet's atmosphere away, layer by layer, over vast stretches of time. Scientists believe the planet is essentially evaporating, trailing a faint comet-like tail of lost atmosphere behind it as it circles. It is a world in the slow, quiet process of disappearing, dissolving back into the light that made it. There is a planet called TRES 2b that reflects less than 1% of the light that falls upon it, making it darker than the darkest coal, darker than black paint, darker than almost any natural material we have ever measured. Scientists are not entirely certain what makes it so absorbing, perhaps sodium or potassium gas in its atmosphere, perhaps some other compound that swallows light almost completely. It drifts through its orbit as a near-perfect sphere of darkness, barely a shadow against the star it circles. Even in the brightness of its own solar system, it is essentially invisible, a world that holds all light quietly within itself. Kepler 16b is a world that orbits not one sun but two, a double star system where the planet traces a slow, wide path around both stars at once, just as the fictional desert world of Tatooine does in a beloved old story. From its surface, if it had one you could stand on, you would watch two suns set one after another, or sometimes together, painting the sky in layered hues. Scientists confirmed this world by watching it dim the light of both stars as it passed in front of them. It is a reminder that the universe sometimes builds the things we once only imagined. There exists a planet designated by astronomers as the companion to a pulsar, a world thought to be composed almost entirely of crystallized carbon, compressed under immense pressure into a structure resembling a diamond the size of a planet. It is the remnant of what was once a star, stripped of its outer layers over billions of years until only this dense, glittering core remained. Scientists believe the interior is a vast lattice of carbon atoms locked in crystalline order, cool and silent and extraordinarily dense. Somewhere out there, a world made of diamond turns slowly in the dark, unhurried and ancient beyond measure. The planet known as HAT P7b carries clouds made not of water droplets or ice, but of corundum, the same mineral that forms sapphires and rubies here on Earth. On its cooler night side, these gem-like crystals condense and drift through the atmosphere, swept by supersonic winds that circle the planet in an endless roaring current. The idea of a sky seeded with sapphire and ruby crystals is almost too luminous to hold in the mind. And yet this is not imagination, it is what the light from that distant world, carefully read by our instruments, suggests is truly there. Long before the moon hung in our sky, scientists believe a planet roughly the size of Mars drifted through the young solar system and collided with the early Earth in a slow, colossal impact. This world, which researchers call Theia, merged with our planet in a vast outpouring of heat and debris, and the material that was flung outward gradually gathered itself into the moon. The collision was not a sudden explosion, but a deep, drawn-out blending, two worlds becoming one and leaving behind a companion that has lit our nights ever since. The moon above you tonight was born from that ancient meeting. The moon is not fixed in its orbit. It is very slowly drifting away from Earth, moving outward by about 3.8 centimeters every year, drawn by the subtle interplay of tidal forces between the two worlds. Over millions of years, this gentle recession will carry the moon measurably farther from us, and the tides it raises on Earth will gradually weaken. For now, the change is imperceptible, softer than a breath, slower than a season. But the moon is always quietly moving on, and the Earth is letting it go, one unhurried centimeter at a time. Hyperion, one of Saturn's many moons, tumbles through its orbit with no fixed axis of rotation. It spins chaotically, tipping and rolling in an unpredictable pattern that scientists cannot forecast far into the future. Its irregular, sponge-like shape and the gravitational nudges it receives from nearby Titan conspire to keep it perpetually off balance. There is something oddly restful about this, in its way, a world that simply drifts and turns without plan, without direction, following only the gentle push of forces around it. It asks nothing of itself. It simply moves. Titan, Saturn's largest moon, is draped in a thick amber haze and holds on its surface something that looks remarkably like a water world. But instead of water, its lakes and rivers and slow-moving seas are filled with liquid methane and ethane, pooling in low-lying basins near the northern pole. The landscape is shaped by these hydrocarbon rains and floods, carving channels and deltas into the icy ground, just as rivers carve valleys here on Earth. It is a world with weather, with seasons, with a slow hydrological cycle, but one built entirely from chemistry that would be poisonous to us. And yet it is beautiful, in its own amber, unhurried way. Let yourself settle now, just a little more deeply. Feel the weight of your body resting where you lie, fully supported, fully held. There is nowhere to go and nothing to tend to. Let each breath come and go on its own, slow and unhurried. Let your thoughts drift, like distant clouds moving across a wide, still sky, noticed and then released. You are safe. You are resting. The universe continues its slow and wondrous turning, and all you need to do right now is let go. Beneath the frozen shell of Enceladus, one of Saturn's smaller moons, a liquid ocean lies hidden in the dark, and from cracks near its southern pole, that ocean vents itself into space as towering plumes of water vapor and ice crystals. These geysers rise hundreds of kilometers above the surface, arcing outward into Saturn's rings and scattering into the void. The water is warm, laced with minerals, and scientists believe it may hold the conditions needed for life. A small, pale moon quietly exhaling into the cosmos. Miranda, a small moon of Uranus, carries upon its surface a cliff so immense it is difficult to fully hold in the mind, a sheer vertical drop of 20 kilometers, the tallest known cliff face in the entire solar system. Standing at its edge, you would look down into a chasm so deep that a stone dropped from the top would take about 10 minutes to reach the bottom in Miranda's faint gravity. The cliff is ancient, carved by forces scientists are still piecing together. It stands in utter silence, under a sky in which the sun appears as little more than a bright star. Io, one of Jupiter's 4 large moons, is the most volcanically restless world in the solar system, its surface perpetually reshaped by hundreds of active volcanoes, erupting sulfur and silicate rock in plumes that rise hundreds of kilometers high. This relentless activity is driven not by internal heat left over from formation, but by the gravitational tug-of-war between Jupiter and its neighboring moons, which kneads Io's interior like dough, generating enormous friction and heat. The surface glows in patches of orange, yellow, and black, a world that never cools, never rests, endlessly renewing itself. Beneath the cracked and fractured ice shell of Europa, another of Jupiter's moons, a vast liquid ocean stretches in all directions, and that ocean holds roughly twice as much water as all of Earth's oceans combined. The ice above it is riddled with reddish-brown lines where warmer material from below has seeped upward and refrozen, tracing a record of slow movement across the surface. Scientists believe this hidden sea, kept liquid by tidal heating, could be one of the most promising places in the solar system to search for life. An ocean world sealed away in ice, carrying more water than our entire blue planet. Pluto, drifting in the cold outer reaches of the solar system, carries upon its surface vast plains of nitrogen ice that flow and creep like glaciers on Earth, but at temperatures of around -230 degrees Celsius, colder than almost anywhere else in the solar system. These glaciers move not because of warmth, but because of the slow, subtle pressure of their own weight, spreading across ancient impact basins in pale, billowing shapes. When the New Horizons spacecraft swept past Pluto, it revealed a world far more alive and intricate than anyone had imagined, a place of haze layers, mountain ranges, and these slow, ghostly rivers of frozen nitrogen. Far beyond the planets, in the outermost reaches of the solar system, a small frozen world called Arokoth drifts in perpetual darkness, and it holds the distinction of being the most distant object ever visited by a spacecraft. When the New Horizons probe reached it, the images revealed something wonderfully unexpected. Two rounded lobes joined at a narrow neck, giving it the unmistakable shape of a snowman. This gentle, double-lobed form tells scientists that the two halves came together slowly and softly, orbiting each other for a long time before drifting into a tender embrace. It is ancient, undisturbed, and impossibly far from home. In the autumn of 2017, astronomers tracked a visitor passing through the solar system from interstellar space, a thin, tumbling object they named Oumuamua. As it swung around the sun and headed back out into the void, something unexpected happened. It accelerated, departing faster than the sun's gravity alone could explain. Comets sometimes show this kind of push from outgassing vapor, but no such gases were ever detected from Oumuamua. Scientists believe a process similar to outgassing, perhaps involving hydrogen, may account for it, though the question lingers quietly, like a note held just a moment too long. The universe offered no easy answer, only wonder. Oumuamua was not only unusual in its motion, its shape was unlike anything seen before in our solar system. Observations suggested it was extraordinarily elongated, perhaps 10 times as long as it was wide, tumbling end over end through space. No known asteroid or comet from our own system comes close to such proportions. Whether it was a shard of rock, a fragment of a shattered planet from another star, or something else entirely, scientists are still not certain. It passed through our neighborhood briefly, revealed only a silhouette of itself, and then moved on, back into the immensity of interstellar space, carrying its secrets with it. 2 years after Oumuamua's passage, a second visitor arrived from beyond our solar system, a comet named Borisov, the first confirmed interstellar comet ever observed. Unlike Oumuamua, Borisov looked reassuringly familiar. It bore a small glowing coma of gas and dust, a modest tail, and a composition that resembled comets from our own system. It passed through, made its closest approach to the sun, and continued outward, carrying with it material forged around another star in another part of the galaxy. The universe, it seems, is not as separate as it once appeared. Its pieces drift between the stars, visiting one another across the long, unhurried stretches of time. The sun's outer atmosphere, its corona, burns at temperatures reaching several million degrees Celsius, far hotter than the visible surface below it, which sits at a comparatively modest 6,000 degrees. This reversal of temperature with distance is one of the most enduring puzzles in solar science. Scientists believe waves of energy, rippling through magnetic field lines, may carry heat outward into the corona, but the precise mechanism remains elusive. The corona glows like a crown of white fire during a total eclipse, achingly beautiful and still, in its own way, mysterious. It is a warmth that defies the ordinary rules, hovering above the sun like a question the universe has not yet fully answered. Let yourself rest now. There is nothing left to figure out tonight, nothing to solve or remember. Simply notice the weight of your body, how it settles a little more with each breath. Let your shoulders drop. Let your hands open. Each exhale carries away a little more of the day, and each inhale brings something quieter in its place. You are safe and still and held. Let the mind grow soft at its edges. There is only this breath, and then the next, and then the long, unhurried drift towards sleep. Among the most extreme objects in the known universe are magnetars, a rare variety of neutron star wrapped in a magnetic field of almost incomprehensible strength. In a single millisecond, a magnetar can release more energy than our sun will radiate across 100,000 years. That figure is so vast, it barely registers as a number. It is more like a different category of existence altogether. These bursts arrive as waves of gamma rays and X-rays crossing the galaxy at the speed of light. The universe, for all its vast silences, carries within it these brief, incandescent moments of unimaginable release. If magnetars seem extraordinary, gamma-ray bursts reach beyond even that scale. In a matter of seconds, sometimes less, a single gamma-ray burst releases more energy than our sun will produce across its entire 10 billion-year lifetime. They are the most luminous events known to occur in the universe, thought to arise from the collapse of massive stars or the merger of dense stellar remnants. They last only moments, blazing across billions of light-years of space, and then they are gone. The light from one of these events, traveling toward us across the cosmos, carries with it the memory of a star's final, radiant breath. Scattered across the sky like brief, brilliant sparks are fast radio bursts, millisecond flashes of radio energy arriving from enormous distances across the universe. In a fraction of a second, each one releases as much radio energy as the sun produces in days. They come from all directions, from galaxies billions of light-years away, and they vanish before any instrument can fully trace their origin. Scientists have linked some to magnetars, but others remain unaccounted for. They are fleeting whispers from the deep universe, arriving without introduction, departing without explanation, brief and luminous and wonderfully, quietly strange. Among the many fast radio bursts detected, a handful have done something that sets them apart from the rest. They repeat, and not just at random intervals, but in patterns, cycling with a regularity that has drawn the careful attention of researchers. Some repeat every few days, others over longer stretches, as though governed by some underlying rhythm. Most scientists believe these patterns arise from natural astrophysical processes, perhaps a neutron, star orbiting a companion, or precessing as it spins. The explanations are almost certainly natural, and yet the patterns linger in the mind like a soft, recurring melody heard from a great and unknowable distance. In the summer of 1977, an astronomer scanning data from a radio telescope in Ohio noticed something that stopped him. A signal had arrived, 72 seconds long, narrow in frequency, and so striking in its characteristics that he circled it on the printout and wrote a single word beside it: "Wow." The signal matched what scientists had theorized an extraterrestrial transmission might look like. It has never been detected again, despite many searches. Its origin remains unresolved. Scientists have proposed natural explanations, comets, hydrogen clouds, but none has fully satisfied everyone. It arrived once, left its mark on a strip of paper, and then the sky went quiet again. Stephen Hawking predicted that black holes are not entirely silent, that they slowly release a faint thermal radiation born from quantum effects at the event horizon. This radiation, known as Hawking radiation, would cause a black hole to lose mass over immense stretches of time and eventually evaporate entirely. It is one of the most celebrated theoretical predictions in modern physics, and yet no instrument has ever detected it directly. The radiation from stellar mass black holes would be so faint as to be buried beneath the background glow of the universe itself. It may remain beyond our reach for as long as our current technology endures. A beautiful idea, real in mathematics, invisible in the sky. The universe is old enough and large enough to hold billions of worlds where life might conceivably arise, and yet, when we listen, with radio telescopes, with careful instruments, with decades of patient searching, the sky is silent. No signal, no beacon, no sign of another civilization reaching outward. This quiet has a name, the Fermi paradox, after the physicist who once asked, simply and famously, "Where is everyone?" There are many possible answers, and scientists hold them gently. Perhaps life is rarer than we imagine. Perhaps civilizations are brief. Perhaps the distances are simply too vast. The silence is not frightening. It is only the universe, breathing slowly, keeping its own counsel. There is a thought that surfaces at the far edges of physics and philosophy. What if the universe we inhabit is not the base layer of reality, but a computed one, a simulation of extraordinary depth and detail, running on some substrate we cannot perceive? The simulation hypothesis, as it is known, suggests that an advanced civilization might one day create virtual realities indistinguishable from the real, and that we may already be living inside one. It cannot be proven or disproven with current tools. Scientists and philosophers hold it as a possibility, not a certainty, a strange mirror held up to existence. And whether it is true or not, the universe we find ourselves in is no less wondrous for the asking. The many worlds interpretation states that every quantum measurement splits the universe into parallel branches. According to this idea, nothing is ever truly decided. Every possibility simply continues, unfolding in its own separate reality. When a particle chooses one path, another version of the universe quietly branches off, carrying the other path forward. There is no collapse, no single outcome, only an ever-widening tree of coexisting worlds. Each branch is as real as our own, drifting silently away from us, beyond all reach or observation. The landscape of string theory predicts an almost incomprehensible number of possible universes, 10 raised to the power of 500, each governed by its own distinct physical laws. That number is so vast it dwarfs any quantity we encounter in ordinary life, larger than the count of atoms in the observable universe many times over. Each point in this theoretical landscape represents a different reality, a different set of rules, a different way existence could have arranged itself. Our universe is just one valley in a terrain of infinite variety, resting quietly in its own particular configuration of forces and constants. Let your body settle a little more deeply into wherever you are resting. There is nothing to hold on to right now, nothing to figure out. Let your breath move slowly and easily, in and out, without any effort at all. Feel the weight of your limbs growing heavier, softer, more at ease. Your thoughts can drift wherever they like. They do not need to be followed. Simply rest here, unhurried, in the quiet. The universe is vast and patient, and tonight, so are you. Eternal inflation theory suggests that our Big Bang was not a singular beginning, but one of countless such events still unfolding across a larger, ever-expanding substrate of space. In this picture, bubble universes are constantly nucleating, each one a new cosmos, sealed off from all the others, carrying its own history forward from its own moment of origin. Our entire observable universe, with all its billions of galaxies and billions of years, may be just one small bubble adrift in a far vaster sea that never stops giving rise to new worlds. In some of those bubble universes, a fundamental quantity known as the fine structure constant, a number that governs how electrons and light interact, could take a different value entirely. If that constant shifted even slightly, the delicate architecture of atoms would become impossible. Electrons would not bind to nuclei. Chemistry would have no foundation. Molecules, compounds, stars, and living things would never arise. Entire universes may exist in which matter, as we know it, simply never assembles. Vast, silent, structureless expanses where the conditions for complexity never arrive. A universe with even slightly more dark energy than our own would expand so rapidly that matter could never gather into galaxies. Clouds of gas would be pulled apart before gravity could draw them together. Stars would never ignite. Planets would never form. The universe would race outward in every direction, growing thinner and colder with each passing moment, a vast and featureless expanse of spreading emptiness. The light entering your eyes tonight left its source in a universe precisely balanced enough for that source to exist at all. A universe with only slightly stronger gravity than our own would tell a very different story. Rather than expanding outward for billions of years, it would slow, halt, and then fall back inward, collapsing under its own weight almost before it had truly begun. Stars and galaxies might never have time to form. The whole cosmos would compress back toward a singularity in what might amount to a cosmic heartbeat, a universe that opened and closed before it ever had the chance to grow complex or still. The anthropic principle offers a gentle and grounding observation. We find ourselves in a universe that permits our existence precisely because only such a universe could be observed by anyone at all. Of the vast range of possible physical laws and constants, the ones we measure are those compatible with stars, planets, chemistry, and minds. It is not that the universe was made for us. It is simply that we could only ever arise in a place like this. Our presence here is its own quiet evidence that the conditions were right. One possible fate for the universe is known as the Big Rip. If dark energy continues to grow stronger over time, it could eventually overwhelm every other force in existence. Galaxies would be torn apart first, then solar systems, then planets, then individual atoms. The very fabric of space-time would be stretched beyond all coherence. It would happen slowly, over an almost unimaginable span of time, not as a catastrophe, but as a gradual dissolution, the universe growing quieter and more dispersed with each passing age until even the smallest structures can no longer hold. The Big Freeze describes another possible ending, perhaps the most serene of all the universe's imagined fates. Over an almost incomprehensible span of time, stars will exhaust their fuel and fade. Black holes will evaporate. All energy will spread evenly through an ever-expanding space until no temperature difference remains anywhere. No motion, no reaction, no light. The universe will have reached a state of perfect equilibrium, not violent, not sudden, but deeply, utterly still. A silence so complete it becomes a kind of peace. The Big Crunch would reverse the universe's expansion and collapse everything back into a single point. If gravity were ever to overcome the outward push of dark energy, the expansion we see today would slow, halt, and then reverse. Galaxies would draw toward one another. Space itself would contract. Over unimaginable ages, all of existence would fall inward. Stars, light, time, gathering back into the profound stillness of a single, infinitely dense point from which it all once began. Poincaré recurrence theorem holds that in a sufficiently vast and long-lived system, every possible arrangement of matter and energy will eventually recur. Given enough time, far more time than the current age of the universe could, in principle, return to a configuration nearly identical to any moment in its past, not by any mysterious force, but simply by the mathematics of finite states and infinite time. Every pattern, every arrangement of atoms, every quiet moment, all of it, in time, revisited. A Boltzmann brain is a remarkable and strange idea. A self-aware mind that could, in theory, arise spontaneously from the random churning of quantum fluctuations in empty space. Given enough time and enough vacuum, the mathematics of probability allows for almost anything to assemble itself, however briefly. An entire conscious observer, complete with memories and sensations, flickering into existence for a single moment before dissolving back into the void. Scientists consider it a genuine philosophical puzzle, a quiet reminder that awareness itself is a deeply improbable and extraordinary thing. Let your body settle now, just a little more. There is nothing to hold on to, nothing to work out or remember. Let your shoulders drop, let your hands rest, open and easy. Your breath is slow, and even there is no effort in it at all. The thoughts that drift through your mind are like wisps of cloud moving across a very wide sky. You do not need to follow them. Simply rest here in the warmth and the stillness and let yourself drift softly toward sleep. If Boltzmann brains can arise from random fluctuation, then in a universe of truly infinite duration, they would form with staggering frequency, far outnumbering minds like ours that evolved slowly through billions of years of cosmic history. This is not a cause for unease, but a source of quiet wonder. It suggests that the kind of awareness we carry, built patiently by stars and chemistry and time, is something rare and extraordinary. We are not accidental sparks. We are the long, careful work of an entire universe. The universe's most likely final chapter is a cold, dark, and utterly silent void, a stillness so deep and so prolonged that no number we have ever named could measure its duration. All stars gone, all black holes evaporated into faint whispers of radiation, all motion stilled, and yet even this immensity of quiet is a kind of wonder, the universe resting, at last, in perfect and complete repose. You are here, now, in the warm middle of it all. Let that be enough. Let yourself be still. Sleep well and gently. Good night.